Today we're going to learn about transformations of log functions. Now we've done transformations of every function, so the transformation part is the same, just a new function we're transforming. So just a refresher, here's our exponential 2 to the x. So remember the table for this one, and it has an asymptote at y equals 0. So 2 to the x is our exponential growth. It looks something like that. When we take the inverse of that, we get the log base 2 of x, which is the same table, just x's and y's are flipped. So if you know your exponential table, you don't have to memorize this one because you can always come up with it. And know that in your log function, the asymptote is at x equals 0. So this time it's going a different direction. All right, the first set of tables has to do with transformations, reflections. So we're going to take a look at these. If you look carefully, you can see there's some negatives here. That's a negative. That way we can identify these. So the first one we're looking at is f of x equals log base 2 of x. Which one of these looks just like the parent function? I'm going to go with letter B. We're going to call this one f of x. G of x is negative log base 2 of x, so that's a reflection over the x-axis. So you look at your graphs, which one is this but reflected over the x-axis? I would have to go with letter C. Letter H, log base 2 of negative x, that's a reflection over the y-axis. So that one's shifting from left to right. And I think that would go with letter D. And that leaves letter A would be the reflection over the x and over the y. We would end up with this graph. So that was just a quick rehash over reflections. Let's do some actual real reflections or real transformations and have a lot of stuff going on. So we'll start with this one. State the transformations, make a table and graph, state the domain and range, and end behavior. So looking at my function, I noticed the negative. It's a vertical reflection over the x-axis. Remember, reflections come first. Next come dilation, so stretch or compression. The 2 represents a vertical stretch by a scale factor of 2. And -3 is a vertical translation going down 3. So notice there are no horizontal changes on this one. Now to make our transformation table, for me, I'm going to start with my exponential graph, and then I'm going to work my way to the log. Notice there's no base here, and we know if there's no base, it's automatically at base 10. So I know this table really well, so I can write this one down, and my asymptote is at y equals 0. So now I can easily make the log table, now that I know this one. If you have the log table memorized, you can skip that one. So I'm going to draw the table for y equals log x, which is just the inverse of the table I just wrote. And this time the asymptote is at x equals 0. So now this is the table I'm going to transform, the log table. There were no horizontal changes, so x stayed the same. So x is still 1/10, 1, and 10, and x equals 0. No changes there. The vertical changes are all going in the y. It's a reflection, it's a stretch, and it's down 3. And now all I have to do is plug my y values from my log function into my transform table. -2 times -1 is 2, -3, -1. Plug in 0 and plug in 1. Now I'm ready to graph from my transform table. 1/10 -1, 1 -3, and 10 -5. And remember my vertical asymptote was x equals 0, so I'm approaching but not actually touching x equals 0. And there's the graph of -2 log x minus 3. So this is the table we're expecting you to see, not some decimals off your calculator. So we want to make sure you know how to write the transformed rules and the transform table. Domain. What is the domain of this function? Looks like it's going from 0 to infinity. Range. Remember the range of our logarithm functions? All real numbers, negative infinity to infinity. End behavior, we have two pieces. On the left side, x is approaching 0. K of x is approaching infinity. And on the other end, as x approaches infinity, k of x is also approaching infinity. All right, let's keep practicing. Same thing. State the transformations, make a table and graph. This one, notice, is a natural log, so that's going to make a different table because it's a different base. But notice what I have to do first. I have to isolate that x. So I'm going to factor out the -2, and that'll leave me with x minus 3. So I'll just rewrite the whole thing. And now we can talk about our transformations. Don't forget to isolate that x. In fact, if there's a number in front of x, factor that out every time. So we'll start with any reflections. I see a vertical reflection over the x-axis. And is there a horizontal reflection? Yes, there is, over the y-axis. Now I look for stretches and compressions. I see a vertical stretch by a scale factor of 4. And there's a 2. Is that a stretch or a compression? It's a compression by a scale factor of 0.5. Remember, everything in the parentheses is opposite land, so be careful with that. The -3 is a horizontal translation to the right, and the +2 at the end is a vertical translation up. There's a lot of translations going on here. Now, I'll be honest, I don't have the table for natural log memorized, so I'm going to start with e to the x and make a table, and then I'll do the same thing I did above. I'll make the natural log table, and then I'll transform that. I know this is -1, 0, 1. I know the asymptote is y equals 0. What I don't know is what e to the -1 equals. So I will look that up. E to the -1, 0.368. I know e to the 0 is 1, and I know e to the 1 is 2.718. I just have that one memorized, but here it is, 2.718. So that's my e to the x table. Now I'm going to do my natural log table, which is just the inverse. So flip all the numbers. 0.368, -1, 1, 0, 2.718, 1. And the inverse has an asymptote at x equals 0. And now I'm ready to do some transformations. Okay, these may not be pretty, but we'll get them done. So for my transformed table, remember all the horizontals go with the x, all the verticals go with the y. Horizontal reflection, negative. Horizontal compression, 1/2 x. To the right, 3. Vertical reflection, vertical stretch, up 2. Remember, we are always looking for those rules. And now we plug these numbers in for x and y and get our new table. So 0.368 times -0.5 plus 3 is 2.816. -0.5 times 1 is -0.5 plus 3 is 2.5. And then -1/2 times 2.718 plus 3 is 1.641. And now we plug in our y's. -1 times -4 plus 2. 0 times -4 plus 2. 1 times -4 plus 2. Now the asymptote here was x equals 0. So when I plug in 0, I get x equals 3 for my asymptote for my new graph. So here goes. 2.816, that's close to 3, and it goes up to 6. 2.5 goes up to 2. And then 1.64 is at negative 2. And my asymptote is x equals 3. So I know that's the line I'm approaching but never touching. It looks kind of like that. So let's talk domain, range, and end behavior. Domain, negative infinity up to 3. And remember, 3 is in parentheses because it's not included. Range, all real numbers. That one doesn't change. Now my end behavior. I have x on the left approaching negative infinity, and z of x also approaching negative infinity. On the right-hand side, x is approaching 3, not approaching infinity this time. So as x is approaching 3, z of x is approaching infinity. So there were a lot of really important things in that one, starting with isolating your x, exponential table, log table, transform table. So just take your time, walk through step by step, and you will be okay. All right, these are interesting. It says analyze the graph, describe the transformations performed on f of x to create the transformed function, write an equation for the transform function in terms of f of x and in terms of x. So let's take a look at f of x, and notice the points on this one. I've got 0, 1 right here, and over here I've got 3, 1. So that makes me think that this one is log base 3. Well, they actually told me that. So let's look at m of x. If you look, you can count. This went over 2, up 1. This one went over 2, up 1. It doesn't look like there's a reflection. There's not a dilation. It just went to the left 1, 2, 3, 4, 5 spaces. So left, 5. What they want us to do is to write the equation two ways. They want us to write m of x in terms of f of x. So if I go to the left 5, I would express that as f of x plus 5. That's what they mean by in terms of f of x. Now to write it in terms of x, I'm going to take the actual function and say that m of x equals log base 3 of x plus 5. I would write the actual log function there. So in terms of f of x and then in terms of x. All right, let's look at the next one. This one is log base 4 of x. We could tell by counting over, it goes to 4, 1. And now let's look at w of x. It does this 1, 2, 3, up 1, 1, 2, 3, up 1. So there's no reflection, there's no dilation. It just moved to the right 1 and up 2. So right 1, up 2. So let's write w of x in terms of f of x. So if I go to the right 1, that should look like x minus 1, and then up 2. That's in terms of f of x. Now we'll write the actual function in terms of x, and that would be log base 4 of x minus 1, and then plus 2. So instead of the f, I actually wrote the function. All right, let's do the next one. This one gets a little bit crazy. So this is log base 3 of x. You can tell because I went to the 3, 1. Now if you look at the p of x function, there's a lot of things changing. So I'm going to look at some key points. On f of x, I've got 1, 0, and 3, 1 as coordinates. Let's look at the coordinates that p of x has. P of x also goes through 1, 0, but this point over here is at 3, 4. So I notice a change from a y-coordinate of 1 to a y-coordinate of 4. That's going to lead me to say it's a vertical stretch by a scale factor of 4, because I took this y-coordinate and multiplied it by 4. So that's how I compare to get something like that. So P of x in terms of f of x, it's a vertical stretch by 4, so it's 4 f of x. In terms of x, P of x is going to equal 4 log base 3 of x, because there were no other transformations happening there. So that's just a little bit of a dig into some transformations. So you're going to apply all of your knowledge from previous transformations to your transformations of logarithms as well.